A photon is an elementary particle, the quantum of light and all other forms of electromagnetic radiation. It is the force carrier for the electromagnetic force, even when static via virtual photons. The effects of this force are easily observable at the microscopic and at the macroscopic level. Because the photon has zero rest mass, this allows long-distance interactions. Like all elementary particles, photons are currently best explained by quantum mechanics and exhibit wave-particle duality, exhibiting properties of waves inner particles. For example, a single photon may be refracted by a lens or exhibit wave interference with itself, but also act as a particle, giving a definite result when its position is measured. Waves and quanta, being two observable aspects of a single phenomenon, cannot have their true nature described in terms of any mechanical model. A representation of this dual property of light, which assumes certain points on the wavefront to be the seat of the energy, is also impossible. Thus, the quanta in a light wave cannot be spatially localized. Some defined physical parameters of a photon are listed. The modern photon concept was developed gradually by Albert Einstein in the first years of the 20th century to explain experimental observations that did not fit the classical wave model of light. In particular, the photon model accounted for the frequency dependence of light's energy, and explained the ability of matter and radiation to be in thermal equilibrium. It also accounted for anomalous observations, including the properties of black-body radiation, that other physicists, most notably Max Planck, had sought to explain using semi-classical models, in which light is still described by Maxwell's equations. But the material objects that emit and absorb light do so in amounts of energy that are quantized. Although these semi-classical models contributed to the development of quantum mechanics, many further experiments, starting with Compton's scattering of single photons by electrons, first observed in 1923, validated Einstein's hypothesis that light itself is quantized. In 1926, the optical physicist Fritjof Wolfers and the chemist Gilbert N. Lewis coined the name photon for these particles, and after 1927, when Arthur H. Compton won the Nobel Prize for his scattering studies, most scientists accepted the validity that quanta of light have an independent existence, and the term photon for light quanta was accepted. In the standard model of particle physics, photons and other elementary particles are described as a necessary consequence of physical laws having a certain symmetry at every point in space-time. The intrinsic properties of particles, such as charge, mass and spin, are determined by the properties of this gauge symmetry. The photon concept has led to momentous advances in experimental and theoretical physics, such as lasers, Bose-Einstein condensation, quantum field theory, and the probabilistic interpretation of quantum mechanics. It has been applied to photochemistry, high-resolution microscopy, and measurements of molecular distances. Recently, photons have been studied as elements of quantum computers and for applications in optical imaging and optical communication such as quantum cryptography. Nomenclature. In 1900, the German physicist Max Planck was working on black-body radiation and suggested that the energy in electromagnetic waves could only be released in packets of energy. In his 1901 article in Annalen der Physik, he called these packets energy elements. The word quanta was used even before 1900 to mean particles or amounts of different quantities, including electricity. Later, in 1905, Albert Einstein went further by suggesting that electromagnetic waves could only exist in these discrete wave packets. He called such a wave packet the light quantum. The name photon derives from the Greek word for light, phi sigma. Arthur Compton used photon in 1928, referring to Gilbert N. Lewis. The same name was used earlier by the American physicist and psychologist Leonard T. Troland, who coined the word in 1916, in 1921 by the Irish physicist John Joly, in 1924 by the French physiologist René Wormser, and in 1926 by the French physicist Fritjof Wolfers. The name was suggested initially as a unit related to the illumination of the eye and the resulting sensation of light, and was used later on in a physiological context. Although Wolfers's and Lewis's theories were never accepted, as they were contradicted by many experiments, the new name was adopted very soon by most physicists after Compton used it. In physics, a photon is usually denoted by the symbol gamma. This symbol for the photon probably derives from gamma rays, which were discovered in 1900 by Paul Villard, named by Ernest Rutherford in 1903, and shown to be a form of electromagnetic radiation in 1914 by Rutherford and Edward Andrade. In chemistry and optical engineering, photons are usually symbolized by h nu, the energy of a photon, where h is Planck's constant and the Greek letter nu is the photon's frequency. Much less commonly, the photon can be symbolized by hf, where its frequency is denoted by f. Physical properties. A photon is massless, has no electric charge, and is stable. A photon has two possible polarization states. In the momentum representation, which is preferred in quantum field theory, a photon is described by its wave vector, which determines its wavelength lambda and its direction of propagation. A photon's wave vector may not be zero and can be represented either as a spatial 3-vector or as a 4-vector. In the latter case it belongs to the light cone. Different signs of the 4-vector denote different circular polarizations. But in the 3-vector representation one should account for the polarization state separately. It actually is a spin quantum number. In both cases the space of possible wave vectors is 3-dimensional. The photon is the gauge boson for electromagnetism, and therefore all other quantum numbers of the photon are zero. Also, the photon does not obey the Pauli exclusion principle. Photons are emitted in many natural processes. For example, when a charge is accelerated it emits synchrotron radiation. During a molecular, atomic or nuclear transition to a lower energy level, photons of various energy will be emitted, from radio waves to gamma rays. A photon can also be emitted when a particle and its corresponding antiparticle are annihilated. In empty space, the photon moves at c and its energy and momentum are related by E equals pc, where p is the magnitude of the momentum vector p. This derives from the following relativistic relation, with m equals 0. The energy and momentum of a photon depend only on its frequency, or inversely, its wavelength. Where k is the wave vector, omega equals 2 pi nu is the angular frequency, and h equals h. 2 pi is the reduced Planck constant. Since p points in the direction of the photon's propagation, the magnitude of the momentum as the photon also carries spin angular momentum that does not depend on its frequency. The magnitude of its spin is and the component measured along its direction of motion, its helicity, must be plus or minus h. These two possible helicities, called right-handed and left-handed, correspond to the two possible circular polarization states of the photon. To illustrate the significance of these formulae, the annihilation of a particle with its antiparticle in free space must result in the creation of at least two photons for the following reason. In the center of momentum frame, the colliding antiparticles have no net momentum, whereas a single photon always has momentum. Hence, conservation of momentum requires that at least two photons are created, with zero net momentum. The energy of the two photons, or, equivalently, their frequency, may be determined from conservation of 4 momentum. Seen another way, the photon can be considered as its own antiparticle. The reverse process, pair production, is the dominant mechanism by which high-energy photons such as gamma rays lose energy while passing through matter. That process is the reversive annihilation to one photon, allowed in the electric field of an atomic nucleus. The classical formulae for the energy and momentum of electromagnetic radiation can be re-expressed in terms of photon events. For example, the pressure of electromagnetic radiation on an object derives from the transfer of photon momentum per unit time in unit area to that object. Since pressure is force per unit area and force is the change in momentum per unit time, experimental checks on photon mass current commonly accepted physical theories imply or assume the photon to be strictly massless. If the photon is not a strictly massless particle, it would not move at the exact speed of light in vacuum. Its speed would be lower and depend on its frequency. Relativity would be unaffected by this. The so-called speed of light, c, would then not be the actual speed at which light moves, but a constant of nature which is the maximum speed that any object could theoretically attain in space-time. Thus, it would still be the speed of space-time ripples, but it would not be the speed of photons. If a photon did have non-zero mass, there would be other effects as well. Coulomb's law would be modified and the electromagnetic field would have an extra physical degree of freedom. These effects yield more sensitive experimental probes of the photon mass than the frequency dependence of the speed of light. If Coulomb's law is not exactly valid, then that would cause the presence of an electric field inside a hollow conductor when it is subjected to an external electric field. This thus allows one to test Coulomb's law to very high precision. A null result of such an experiment has set a limit of m10-14 electron volts, C2. Sharper upper limits have been obtained in experiments designed to detect effects caused by the galactic vector potential. Although the galactic vector potential is very large because the galactic magnetic field exists on very long length scales, only the magnetic field is observable if the photon is massless. In case of a massive photon, the mass term would affect the galactic plasma. The fact that no such effects are seen implies an upper bound on the photon mass of m less than 6973300000000000000000000000000000000000000000000000000000000000000000000000000000000000000 times 10⁻27 electron volts, C2. The galactic vector potential can also be probed directly by measuring the torque exerted on a magnetized ring. Such methods were used to obtain the sharper upper limit of 10⁻18 electron volts, C2 given by the particle data group. These sharp limits from the non-observation of the effects caused by the galactic vector potential have been shown to be model-dependent. If the photon mass is generated via the Higgs mechanism, then the upper limit of m10-14 electron volts, C2 from the test of Coulomb's law is valid. Photons inside superconductors do develop a non-zero effective rest mass. As a result, electromagnetic forces become short-range inside superconductors. Historical development. In most theories up to the 18th century, light was pictured as being made up of particles. Since particle models cannot easily account for the refraction, diffraction and birefringence of light, wave theories of light were proposed by René Descartes, Robert Hooke, and Christian Huygens. However, particle models remain dominant, chiefly due to the influence of Isaac Newton. In the early 19th century, Thomas Young and August Fresnel clearly demonstrated the interference and diffraction of light, and by 1850 wave models were generally accepted. In 1865, James Clerk Maxwell's prediction that light was an electromagnetic wave, which was confirmed experimentally in 1888 by Heinrich Hertz's detection of radio waves, seemed to be the final blow to particle models of light. The Maxwell wave theory, however, does not account for all properties of light. The Maxwell theory predicts that the energy of a light wave depends only on its intensity, not on its frequency. Nevertheless, several independent types of experiments show that the energy imparted by light to atoms depends only on the light's frequency, not on its intensity. For example, some chemical reactions are provoked only by light of frequency higher than a certain threshold. Light of frequency lower than the threshold, no matter how intense, does not initiate the reaction. Similarly, electrons can be ejected from a metal plate by shining light of sufficiently high frequency on it. The energy of the ejected electron is related only to the light's frequency, not to its intensity. At the same time, investigations of blackbody radiation carried out over 4 decades by various researchers culminated in Max Planck's hypothesis that the energy of any system that absorbs or emits electromagnetic radiation of frequency nu is an integer multiple of an energy quantum E equals h nu, as shown by Albert Einstein. Some form of energy quantization must be assumed to account for the thermal equilibrium observed between matter and electromagnetic radiation. For this explanation of the photoelectric effect, Einstein received the 1921 Nobel Prize in Physics. Since the Maxwell theory of light allows for all possible energies of electromagnetic radiation, most physicists assumed initially that the energy quantization resulted from some unknown constraint on the matter that absorbs or emits the radiation. In 1905, Einstein was the first to propose that energy quantization was a property of electromagnetic radiation itself. Although he accepted the validity of Maxwell's theory, Einstein pointed out that many anomalous experiments could be explained if the energy of a Maxwellian light wave were localized into point-like quanta that move independently of one another, even if the wave itself is spread continuously over space. In 1909 and 1916, Einstein showed that, if Planck's law of blackbody radiation is accepted, the energy quanta must also carry momentum p equals h lambda, making them full-fledged particles. This photon momentum was observed experimentally by Arthur Compton, for which he received the Nobel Prize in 1927. The pivotal question was then, how to unify Maxwell's wave theory of light with its experimentally observed particle nature. The answer to this question occupied Albert Einstein for the rest of his life, and was solved in quantum electrodynamics and its successor, the Standard Model. Einstein's light quantum. Unlike Planck, Einstein entertained the possibility that there might be actual physical quanta of light, what we now call photons. He noticed that a light quantum with energy proportional to its frequency would explain a number of troubling puzzles and paradoxes, including an unpublished law by Stokes, the ultraviolet catastrophe, and of course the photoelectric effect. Stokes's law said simply that the frequency of fluorescent light cannot be greater than the frequency of the light inducing it. Einstein eliminated the ultraviolet catastrophe by imagining a gas of photons behaving like a gas of electrons that he had previously considered. He was advised by a colleague to be careful how he wrote up to this paper, in order to not challenge Planck too directly, as he was a powerful figure, and indeed the warning was justified, as Planck never forgave him for writing it. Early objections. Einstein's 1905 predictions were verified experimentally in several ways in the first 2 decades of the 20th century, as recounted in Robert Millikan's Nobel lecture. However, before Compton's experiment showing that photons carried momentum proportional to their wave number, most physicists were reluctant to believe that electromagnetic radiation itself might be particulate. Instead, there was a widespread belief that energy quantization resulted from some unknown constraint on a matter that absorbs or emits radiation. Attitudes changed over time. In part, the change can be traced to experiments such as Compton's scattering, where it was much more difficult not to ascribe quantization to light itself to explain the observed results. Even after Compton's experiment, Niels Bohr, Hendrik Kramers and John Slater made one last attempt to preserve the Maxwellian continuous electromagnetic field model of light, the so-called BKS model. To account for the data then available, two drastic hypotheses had to be made. Energy and momentum are conserved only on the average in interactions between matter and radiation, not in elementary processes such as absorption and emission. This allows one to reconcile the discontinuously changing energy of the atom with the continuous release of energy into radiation. Causality is abandoned. For example, spontaneous emissions are merely emissions induced by a virtual electromagnetic field. However, refined Compton experiments showed that energy momentum is conserved extraordinarily well in elementary processes, and also that the jolting of the electron and the generation of a new photon in Compton scattering obey causality to within 10 ps. Accordingly, Bohr and his co-workers gave their model as honorable a funeral as possible. Nevertheless, the failures of the BKS model inspired Werner Heisenberg in his development of matrix mechanics. A few physicists persisted in developing semi-classical models in which electromagnetic radiation is not quantized, but matter appears to obey the laws of quantum mechanics. Although the evidence for photons from chemical and physical experiments was overwhelming by the 1970s, this evidence could not be considered as absolutely definitive, since it relied on the interaction of light with matter. A sufficiently complicated theory of matter could in principle account for the evidence. Nevertheless, all semi-classical theories were refuted definitively in the 1970s and 1980s by photon correlation experiments. Hence, Einstein's hypothesis that quantization as a property of light itself is considered to be proven.